Hello, everyone. My name is Alicia, and in this talk, I wanted to share some work that I started during my practicum at Sandia National Labs. So this work is in collaboration with Matthew Grace and Mohan Saravar, both at Sandia, as well as my PhD advisor, Herschel Rabitz at Princeton. So I wanted to begin with a bit of motivation. So my background is in chemical engineering. And in chemical engineering, we often think about controlling chemical processes. And to do that, we think about tuning temperature and pressure in a chemical reactor or varying the ratio of the reactants entering the reactor. But when I started my PhD, I learned about something radically different. And that's the prospect of controlling chemistry with light. And so the idea here is to use lasers to create tailored light, which can control chemical transformations in a way that would not conventionally be possible. And so the way that we might think about that is that given a molecule, given some chemical system, we want to shine our laser light onto it. So this squiggle is representing our light. And we want to design our light such that it can serve as a photonic reagent and create some desired transformation. So one option would be we could snip a selected chemical bond such that as the molecule evolves, we see this dissociation reaction happen. Of course, that's only one possibility. There are numerous other things that we can imagine controlling using lasers. So we could imagine controlling molecular rearrangement, orientation, controlling isotope selective processes, controlling charge and energy transfer, and many more. So this is actually not a new idea. So the idea of controlling chemistry with coherent laser light was born at the same time that lasers were invented back in the 1960s. And in the decades since, we've learned that designing photonic reagents is hard. So to date, only proof of principle experiments have been done. And one major reason for this is that progress is currently limited by the computational difficulty of the simulations that are needed to support experimental efforts in this area. And so in this talk, I'm going to share how we might use quantum computers in the future in order to enable this new brand of chemistry using photonic reagents. So I'm going to start with a little bit of background. So one of the primary frameworks that people use to think about designing photonic reagents is called quantum optimal control. And if I wanted to do a quantum optimal control calculation, it would have two pieces. So first of all, given a laser pulse, given a photonic reagent, I need to be able to evaluate the control performance of that reagent. And then I also need to be able to update it in order to improve that performance. So this is an iterative optimization loop. And so the first way that I might think about evaluating the performance of a given reagent is to take it to the lab and do an experiment with it. So in this photo, this shows some of the optical tables in our lab at Princeton. And the problem with doing things experimentally is that if we have a new quantum control experiment that we want to do, that can often take years to build and years to get working. So if we really want to develop a comprehensive understanding of quantum control and of chemistry with photonic reagents, it's not going to be feasible to do that through experiments alone. So another option, maybe more familiar to this audience, would be to use a computer and to simulate the performance of a given photonic reagent. Now, unfortunately, this is also not very feasible, and that's due to the difficulty of the calculations that are required. So in particular, if I have a chemical system, which typically has lots of interacting chemical degrees of freedom, these systems suffer from the curse of dimensionality, and that the computer memory and runtime costs needed to simulate them scale exponentially in the number of degrees of freedom that are present. So in the rest of this talk, I'm going to share how we might use a quantum computer to alleviate this bottleneck and facilitate quantum control simulations moving forward. So before I dive into that, though, I wanted to give just a very brief primer on quantum computing. So first, classical computing. So the idea is to store information in bits. These can be 0 or 1, and then to do logical operations on these bits. So quantum computing is not so different. The idea is to store bits in the state of a quantum object, so a quantum bit or a qubit, and then again to do logical operations on those qubits. So if I wanted to describe a calculation on a quantum computer, it would have 3 stages typically. And so the first stage is to initialize our qubits in a specified initial state. So these arrows are sort of a way to visualize a qubit. So if an arrow is up, it represents 0. If it's down, it represents 1. The next step is to actually do the computation. So this is done by applying a sequence of quantum logic gates to the qubits. And this is really the quantum piece of quantum computing. And then the final step is to read out the results by measuring the qubits. And so here it looks like our quantum gates had the effect of flipping the middle qubit to the 1 state. Now in the 1990s, there were a series of landmark papers showing that quantum computers would offer a meaningful speed up for certain really important problems. And then today, there's a lot of global interest in building quantum computers in order to realize these speed ups at scale. Now we're not quite there yet, but today, nevertheless, there is intense interest in what are called hybrid quantum classical algorithms, and these try to take advantage of the computing potential of the quantum computers that we have, which are noisy and imperfect and error-prone, by coupling them to a classical computer and trying to sort of get the best of both worlds in that way. All right, so with that intro to quantum computing, I now want to present one such hybrid quantum classical algorithm for the task of designing photonic reagents. So here's a flow chart. It might look complicated, but essentially the orange pieces are the quantum piece of the algorithm, and then the blue pieces are what the classical computer is responsible for. And I just wanted to sort of step through the different blocks here, starting in the top left. So the first step of quantum optimal control calculation is of course to define the problem. So this entails defining a model for our chemical system and a parameterization for our laser light. The next step would be to define our control target, so what we want our laser light to do to our system. And this is just a cartoon, but we might imagine designing a pulse to orient our molecule according to the black arrow here. And then the last piece is to define an objective function J, which depends on our laser field parameters. And J is going to be used to quantify how well our control target is achieved. Okay, so after we've defined our problem, the next step is to encode it into the language of quantum computers. So this is called qubit encoding. And I'm going to skip the details and just share the takeaway message, which is that encoding our model into qubits is going to provide us exponential memory savings. And just for a little bit of context, if I have a chemical system with m degrees of freedom represented using d dimensions each, so d grid points or d basis functions, on a conventional computer, I would need on the order of d to the m bits, whereas on a quantum computer, I would need m log d qubits. So this is an exponential compression, which is very powerful. And this is one of the, I would say, original motivations for quantum computing, as recognized by Feynman. Okay, so after we've encoded our problem, the next step is to simulate its simulate the dynamics of our system under the influence of our laser field. So here we have the 3 stages that I talked about before. We begin by initializing our system in a state which encodes the initial condition of our chemical system. We then apply a sequence of logic gates in order to simulate the evolution of our system. So again, the big take-home message is that simulating quantum dynamics using a quantum computer, a quantum circuit, provides exponential runtime savings. So we have exponential memory and exponential runtime savings. And so here I just wanted to sort of flash up the recipe for actually doing this, for actually performing the computation where the full computation in order to simulate the controlled dynamics of a chemical system is described by this block U. And then in a series of sort of stages, we can decompose that into sort of simpler and simpler steps, which ultimately result in this block over here, which describes sort of machine instructions for implementing this. And so if we follow this recipe, we will be able to take advantage of the exponential speed up that I mentioned. All right, so after we've simulated the dynamics, we measure our qubits to read out the value of our objective function. If we've converged, we output our results, which are our control parameters describing our photonic reagent. And if not, then we use our classical computer to update the parameters and iterate to convergence. All right, so in my remaining time, I just wanted to share a numerical study that we did about this algorithm. So we considered a model for the Fenner-Matthews-Olsen light harvesting complex in green sulfur bacteria. So our model had 2 chromophores shown here, where the second one is coupled to a vibrational mode. And our objective was to prepare an excitation on the second chromophore. And this is a meaningful thing to study because if we could prepare excitations like this in the lab and then study the subsequent relaxation in the light harvesting complex, that would give us a lot of insights into how photosynthesis proceeds. So in our numerical study, I want to describe a little bit about what we did. So as I referred to before, current quantum computers are not only limited by size and speed, but also by errors. So each of the 3 stages associated with doing a calculation on a quantum computer are in general infected by errors. And so in our study, we explored the feasibility of a meaningful implementation of our hybrid quantum classical algorithm using an error-prone quantum computer. So here are some of our results. So looking first at the top panel, we show our objective function over the course of 25 optimization iterations using a Nelder-Mead strategy. And then there's 3 colors here. So the orange color shows how our objective is minimized when there's no errors. So this would be the ideal case. Then the red curve shows what happens if we have realistic error rates. So the error rates that we actually have today in trapped ion quantum computers. And we see that unfortunately, the performance is not very good. So there's kind of just a barely perceptible change here. And then the blue curve shows the performance when we have optimistic error rates, where these error rates are chosen to reflect where we expect technology to be in the relatively near future. And we see that there is a dramatic improvement compared with the red curve. And then this lower panel shows the trajectories of the optimization plotted on the landscape defined by theta 1 and theta 2. Each of the trajectories start at the black plus sign, and the optimum here is the white X. Again, we see that when we have realistic error rates, the optimization actually goes in the wrong direction with respect to theta 1. But then when we have optimistic error rates, things actually do a much better job And we follow the ideal case pretty closely for the first few iterations. So we were quite encouraged by this, and we certainly hope that a profitable implementation of our algorithm will be possible in the near future. All right, so with that, I want to sum up. So in the beginning, I motivated this talk by explaining that quantum optimal control simulations involving chemical systems are very difficult. This is due in large part to the curse of dimensionality. The advent of quantum computing has the potential to enable scalable simulations of molecular dynamics, so at polynomial cost in memory and in runtime. I then introduced a hybrid quantum classical algorithm for designing optimal laser fields for molecular control, and then talked through an application that we considered to state preparation and light harvesting complexes, and a feasibility study that we did, which explored implementing our algorithm on near-term and current quantum computers. So with that, I want to thank everybody for joining. I want to especially thank my collaborators on this project, Matthew, Mohan, and Hirsch. And then I wanted to give a really big thanks to DOE CSGF, not just for the funding support, but for the opportunity to do a practicum and then a second practicum. It's had a huge impact on my PhD, and thank you to everybody who was a part of the program. And with that, I would be happy to take any questions. Thank you.